but it will be helpful if I have it open anyways. Just some basic ideas I want to give you, and then we'll have a look at some Excel. And if there's time, we can do more physics, but if not, it doesn't matter. I think it's okay. Have you done with Lorraine uncertainty, the delta? You have? What have you learned?
It was different error calculation.
Okay, well, this is what we're going to do today, error calculations. This should be in your lab report, in the analysis part. Yeah. So, let's take a simple example. Well, no, even simpler first. You're measuring the height of a flower. So let's say the height is 30 centimeters. But of course you know that the height is not exactly 30 centimeters because maybe you can't quite read how much it is. So in your mind you know that you could have made a mistake. And we'll call this, we'll say it's 0.25 centimeters. So your answer would be for the flower that the height is 30 plus or minus 0.25 centimeters. So you understand that, don't you? Like this idea. Now, what happens now when you try to measure a person is you have to use the meter stick twice. So the first time you measure, you'll get something like 1 meter, of course, plus or minus 0.25 meters. And then maybe the second time you measure, you get half a meter plus or minus 0.0025 meters. And maybe you think that means the answer is 1.5 meters plus or minus 0.0025 meters. Yes, this part is right, but this part's wrong. So the error, what happens to the error? It's not going to be 0.0025. It'd be, yeah? It'd be 0.005. The error adds as well. So this is like our first rule. So rule 1, if you want to think about it like that, is when you want the error of two measurements, it's the error of the first measurement plus the error of the second measurement. So this should have been plus or minus 0.005 meters. Did you do that with Lorraine?
No.
You sure?
We did like something like this. There wasn't the same explanation. There was no explanation.
Did you know this result anyways?
Yeah, we knew what
how to add them. Yeah?
Actually, we just followed what she actually wrote the whole thing. We just have to add our own values.
Nice, okay. Right. Continue?
Yes.
Yeah. Are you okay? Okay, what about this situation? You measure something, and then you measure something else, and you care about the difference. So this could be x1 with delta x1, and we'll call this x2 with delta x2, and we'll call this here the difference. So we want to know what the difference is. So what do you think the error would be here? Would it be x1, x2?
x1 minus x2 over 2. Oh.
No, not this one. I know why you think that though. So for example,
Delta x1 minus delta x2.
no. So let's say x1 was 1 meter plus or minus 0.01 meter, and let's say x2 was half a meter plus or minus 0.01 meter. You know that these don't minus because this shouldn't, you can't really say this is 0 because that means this was not perfect, this was not perfect, but now this is perfect. No, so it can't be 0. You don't minus the errors. So what do we think we do? Well, in fact, it's still plus together. So the second rule is that if you want the error, the uncertainty in the difference, it's still the uncertainties added together. Yeah. So far, uncertainty only adds. Yeah. Continue? Okay. Now, I'll give you a minute to try and figure this out. So what you're doing here is you want to calculate the area. And here you measure this to be 1 meter plus or minus 0.01 meter. And you measure this side to be 1 meter plus or minus 0.01 meter. And this is area here. So the area will be 1 meter squared plus or minus, and that's the part I want. I want you to think about what it could be. So I'll let you think about this.
0.001?
No.
0.0.
No, think for a minute. Think for a minute. Maybe. Let's have a look. So if you think about it like this, in the worst possibility, what is the smallest the area could be? Well, it could have been 0.99 multiply 0.99. True? That's the smallest possibility. And what would have been the biggest possibility? 1.01 multiply 1.01. So the uncertainty is the difference between the biggest and the smallest possibility we think it reasonably could be. So the uncertainty of the area would be 1.01 squared minus 0.99 squared over 2, which equals 0.02 meters squared. Yeah? Now, there is actually a special way to calculate uncertainty for any formula, which I'll show you now.
So L is
Yeah, so the answer here is 0.02 meters squared. Mhm. Okay, can I go down? Yes? Yes? No. Yes, okay. So suppose you had something like this. T equals 2 pi root L over G. You know you can change that into T squared is 4 pi squared L over G. So you can get, for example, if you want, G equals 4 pi squared L over T squared. But of course, for example, here you don't know the L perfectly, and here you don't know the T perfectly. So the question is, how do these two affect the G on the left? You see what I'm saying? Like, we don't know the values here perfectly. The only thing we know perfectly is this one. So this means here, this will not be perfect, so we have some uncertainty. Do you get what I'm saying? Yeah? So there is a way to calculate the uncertainty here, and I know Lorraine showed you this formula. So, if you have something like this, Z equals, I don't know, A X N Y M, and you have a delta X and a delta Y, and you want the delta Z, you can calculate it like this: delta Z over, do you know what this means if I put a little bar here? No, this means the average of Z. I think I might need to double check something here. Anyways, equals N delta X over average of X squared plus M delta Y over average of Y squared. I'll give you an example now. So what's nice about this formula is a lot of formulas in physics, you can write it in this form. So for example, if I go back to my G formula, I have G equals 4 pi squared L t power minus 2. So this means I can calculate the uncertainty in G equals, over the average for my G in the data, square root, and this is like a 1 here, it's an example, 1 delta L over the average length squared plus minus 2 delta time over average time squared. So if you want, you can just bring this up to the right, and now you have a formula to calculate your error on the G. Yeah? Let's have a look at an example with numbers. So we'll go back to the example with the area. So this is x and this is y. So what's the formula for area? That's x multiply y. So the formula for area is x power 1, y power 1. So uncertainty in area over my area is equal to square root uncertainty in x over x squared plus uncertainty in y over y squared. So in my example, I thought that this was 1 meter, this was 1 meter, but here I had plus or minus 0.01 meter, and here I had plus or minus 0.01 meter. So my answer would be uncertainty in A over 1 meter squared equals 1 over 0.01 over 1 squared plus 0.01 over 1 squared. Well, what I'm doing is I'm writing my formula in this form. So here I just changed it into power 1, power 1. So you can see that the n is 1 and the m is 1 in the formula. I'm using this formula. So if I look here, I can see the n is 1, the m is 1. And there's no number here, but it doesn't matter. Now, I know Lorraine will show you this formula because this is the same one you'll use in chemistry for your lab reports. Or maybe she's shown you it already. Has she? No?
Just show them. They just use this combination and then I actually show what the formula does.
Yeah. Now you notice that the answer I got here was a little bit different to the answer I got earlier. The answer I got earlier was 0.02. In fact, there are many ways to calculate uncertainty, and they won't all give you the same answer. Because you can never know the true answer exactly. So there's just different ways to estimate the answer. So the first formula you did for me That's fine, but it's a little bit too simple. In fact, this one I think is more accurate than the one we did earlier, this formula. Okay, so this is the one that Lorraine will use as well. And the reason we both use this one is this is the simplest formula we could find that is still very accurate. So the other formulas are too simple, and there's many more difficult formulas. If you go to Wikipedia, I think you'll find at least 12 different ways to calculate uncertainty. So this is the easiest non-simple way. So this is why we both use it. Okay, so I'll give you one example to practice, and then we'll have a look at using Excel then, okay? So let's say you have an experiment where you want to calculate or measure, well actually hang on, I know. So you remember the formula OR equals rho L over A. Do you remember this formula? And let's call this here OR. So you have OR equals rho L over pi OR squared. Okay, so here's the information. Let's say the OR is 2 plus or minus 0.1 ohms. Let's say the length is 0.5 plus or minus 0.001 meters. And let's say the OR is 2 plus or minus 0.1 millimeters. So the first question here, A, is calculate resistivity, and then B is estimate the uncertainty in your calculation. Okay, try this one for me. Okay. Did you calculate part A? No. Let me help you. So here you can say resistivity is R pi r squared over L. So in this example it would be 2 pi 0.002 squared over 0.5. So we're just using these numbers first. And don't forget this is millimeters, meters, ohms. Okay, is that part okay? That's just calculation from semester 1. Now, the next part, if you look at this formula, you can write it as this equals pi or power 1 or power minus 2 and L power minus 1. So before I continue, is this one okay, what I did here?
What is the pi at the front?
Oh, it doesn't matter. I like to put the constant in the front. Is that okay? Yeah. So now you know that the uncertainty in this calculation divided by its value, that's equal to square root 1 uncertainty or over or squared plus minus 2 uncertainty of radius over radius squared plus minus 1 uncertainty of L over the L squared. So you get, if you want to bring this up to the right, you get uncertainty of resistivity equals 5.03 times 10 to the minus 5, big square root, 0.1 over 2 squared plus 4 times 0.0001 over 0.002 squared plus 0.001 over 0.5 squared.
The average is just the value.
Yeah, the average is either the value, or if you have a list of data, it's the average of data. But if you don't have the list of data, then the average is the value. I should actually say, so he.
What is the times for?
One sec. I'm being a little bit not so careful with my symbol. So just to be very, very clear, I write this, which means average, okay? But really I should write this, which you might think, what is the difference? This is called my best prediction of X. which is normally either A, the average, or B, a calculation from a formula. So I know I usually write this, but maybe I should really write this, which means it could be the average or the number I got from the formula. It's my best guess of the value. Is that clear, Sally, what you're saying? Yeah. The only reason I use this is because I thought you saw this before in high school. Am I wrong?
No.
You have seen this in high school?
I've never.
Andy? Have you seen this symbol in high school to mean average?
I never.
No? Amanda? You have, yeah? So in Korea then, what symbol do you use to mean average? Average of X? Do you have a symbol you use? Oh, you didn't do this one? Okay. Anyways, we'll go back. So let's calculate. 5.03 times 10 power minus 5 square root So here you get 5.62 times 10 to the minus 6 ohm meters. So your answer would be resistivity equals 5.03 times 10 to the minus 5 plus or minus 5.62 times 10 to the minus 6 ohm meters. ANS. It means answer. Or if you want to be very nice with your units, you could say this equals 50.3 plus or minus 5.62 micro ohm meters. So what you're saying is you think the resistivity could be as small as 44.68 micro ohm meters, or the resistivity could be as big as 55.65 micro ohm meters. So you have two boundaries. Yeah? Yeah? Okay. Can I close this?